Hello, everyone. Thank you for joining today's webinar, Retrofitting Portfolios, Reducing Operational Emissions and the Role of District Energy. This is the third and final webinar in our three-part series, The Transformative Potential of Sustainable Building Retrofits. I am Raven Carter, and I am moderating today's session. We are joined by our presenters, Gina Anand and Jeff Schroeder. We are recording this session and will provide a link to the recording once it's available. And we will allow 10 minutes at the end of the presentation to answer questions. Please type your questions into the Q&A feature throughout this meeting. This live session is registered with AIA CES for continuing professional education. If you are an AIA member and included your AIA number on the registration form, you will receive one AIA LU and a certificate upon completion of this live webinar. If you did not submit your AIA number on the registration form, please email us. This presentation will touch on 4 learning objectives. Our presenters will highlight how scalable retrofit strategies can reduce operational emissions and prepare buildings for future integration with district energy systems. We'll explore how these systems support decarbonization by distributing renewable thermal energy across multiple buildings, examine current investment and policy trends driving their growth, and review recent technological advancements that are enhancing their performance and impact. And with that, I will pass it off to today's presenters.
Hello, everyone, and thank you so much for joining us today. My name is Gina Anand. I'm the Decarbonization Business Lead at Stantec, based in Ottawa. I have more than 14 years of experience, and I'm passionate about regenerative approaches that prioritize people and the planet, and I would love to advance global decarbonization with all innovation frameworks that we currently work with. I'll let Jeff please introduce yourself.
Yeah, Jeff Schroeder, Senior Mechanical Engineer and Practice Lead, specializing in district energy. I have the opportunity of working on district energy projects across the globe, most of it focused in North America, but it's been amazing to see the changes in the industry over the last number of years.
Perfect. So with that, we, in all our presentations, internally and externally, we like to start with a health and safety moment. So for today, we have a safety moment that focuses on noise pollution. So noise pollution from air conditioning units is a growing concern in urban areas. Traditional air conditioning systems create disruptive noise through compressors. We understand that there's constant humming and rattling, and ways to reduce it is basically to understand that there's other ways to introduce, like geothermal HVAC systems. With that, this could use underground piping and water to transfer energy from the ground, and this would remove the need for noisy building level compressors and fans. For individual homes, this really means quieter outer space, and for larger buildings, this may allow for rooftop space to be given back to the occupants to use for new purposes. So the first section of this presentation focuses on portfolio-wide retrofit strategies. We will start by really showcasing how Stantec is a global leader in sustainable engineering, architecture, and environmental consulting. Our technical specialists are at the forefront of innovation that help communities plan for climate change, enhance biodiversity, and environmental health. We provide social value, we develop economic opportunities, and create a sense of space and well-being. And as we take this retrofit journey, it's important to recognize the scale and impact of the Stantec decarbonization efforts. Across North America, we've led more than 40 portfolio-scale decarbonization projects, and those range from university campuses, from healthcare systems to government and commercial portfolios. These initiatives really go beyond individual buildings. They represent a strategic system-level approach to reducing emissions, improving the energy performance, and future-proofing assets. Our approach is holistic and strategic and positions us as trusted advisors, helping clients navigate early stage planning through implementation with a focus on measurable outcomes and long-term sustainability. So with that, we'll move to an interesting slide here that really illustrates a critical mindset shift. On the top, we see common barriers often rooted in the outdated assumptions or rigid thinking. And below, we offer a framed perspective, one that really supports strategic, phase, and technically sound decarbonization. For example, instead of focusing solely on simple payback, we consider long-term capital planning. And when we hear it cannot be done, we ask what can be phased in over time, because incremental progress is really still a progress. And rather than defaulting to one-to-one equipment replacement, we consider the right sizing and the partial electrification, solutions that are really more efficient and future ready. And we also heard about waiting for better technology, which we know that this delays the impact. So instead, we start now with enabling steps like infrastructure upgrades that prepare us for full decarbonization. The phase upgrades, electrification over time, and enabling measures like controls or grid upgrades, these make really decarbonization possible, and they make them really strategically viable. So the message we really have for you today is how we frame a challenge determines the solutions we see and whether we act. And decarbonization is not impossible. It's about shifting the lens from short-term cost to long-term value. So we do acknowledge all the barriers, all the challenges, and yes, there are cost barriers like equipment service upgrades, like space constraints. There are grid barriers like utility delays, resilience concerns, and congestion, and organization barriers, obviously fragmented ownership, lack of expertise and lead structure. But this is really important because these barriers are not really permanent roadblocks. They are input to our planning. They tell us where we need phasing, where we need partnership, and where we need to look for alternative solutions. And if we treat these barriers as a reasons to stop, we lose. If we treat them as a design constraint, we really become the innovators. So this is where carbon meets value. Investors, regulators, and tenants are already prioritizing low carbon buildings. Assets with outdated systems or high carbon footprint, they're becoming less and less attractive, harder to lease, and there's a risk of write-downs. So that's what we call stranded assets, buildings that lose value because they cannot keep up. And retrofits protect against this by aligning performance with market and regulatory expectations. So decarbonization is not just about emissions, it's about protecting asset value and avoiding obsolescence. We are going to start off with an interesting roadmap here to get things done and not just talked about. We establish a framework where we define the goals, scope, timeline, and introduce the right stakeholders to the project. We think about the asset performance where we calculate the baseline emissions, the energy, and the costs. And then we start thinking about how we prioritize measures. Do we think about efficiency, electrification, optimized controls and storage? And then we start drafting a plan. And that plan looks like by summarizing the actions, the triggers, the emission impact, and the infrastructure needs. And then the implement. How do we implement? We do it in phases. We minimize disruption and we communicate with occupants and stakeholders. Do we stop there? No, we track and report. We want to verify performance. Are we doing well? We adjust and we repeat. So we treat this as a cycle and not just as a one-off project. We need to measure, act, improve, and then repeat. So what are the strategies and what really brings us all together today? First, we start with efficiency, and the cheapest ton of carbon is not the one never used. We think about controls, insulation, peak load reduction. We optimize efficiency. We want to make sure efficiency comes first. And then we think about electrification. How can we swap fossil fuel boilers for heat pumps and thermal networks? We think about low global warming potential refrigerants. We want to avoid locking in high global warming potential. How did the market mature? What do we have available and what would work best for our project? We also think of embodied carbon. The materials matter. We need to measure, source smartly, and reduce, and not only for the materials that comes into the envelope, but also for all building systems. We think about the grid interactivity, the demand response, the time of use optimization, and the resiliency part of things. And then we move to the renewables and storage. Are we able to balance the supply and the demand and build for flexibility? So the power is not picking one strategy, it's about combining them into an integrated plan. So again, we're listing more and more on how we do those improvements, whether for existing buildings or for new construction. So operational improvements could look like recommissioning, controls, and metering. They look like envelope upgrades, better roofs, walls, windows, or tightness. We want to cut the demand before we electrify. And then we move to the HVAC. HVAC is really a solid approach to our projects. We bring in mechanical engineers, sustainability expert, and we think about how we shift from electric heat pumps, for example, to smarter controls, efficient humidifier that would integrate, for example, air source and ground source and hybrid systems. And then we think of lighting, we think of hot water, low flow fixtures, electrified systems, renewables, all sorts of renewables. We have a dedicated slide on that. And then the process loads. Are we working with archetypes that do have pools, rings, process heat recovery? You notice that here the strategy is really layered. We build efficiency first, then we electrify, and then we integrate renewables. It's a toolkit. It's not a single measure. So for existing buildings, we need this framework. And from the flow of this presentation, you notice that it's not really random upgrades. We have steps that we start with. Step 0, we start with data. Data is super important. We collect, we build the baseline, and we analyze. And then we move to step 1 to 2, which where we reduce the loads and we maximize the efficiency. Step 3 focuses on electrification of space conditioning and hot water. Step 4 and 5 is where we optimize automation and enable distributed generation. Step 6 and 7, we use storage and connect to the interactive grid. Steps 8 and 9, we weigh the embodied carbon and the financial consideration. We think of this as an ongoing assessment. It's not a checklist. It's a cycle of continuous improvements. And finally, for my section, we really think of widening the lens of energy supply. And there's a menu of clean sources. There's solar, wind, geothermal, hydrogen, biomass, wave, and carbon capture. However, not every building can house every technology, and they don't need to. The real opportunity is district scale systems, shared infrastructure that integrates renewable storage and flexibility across many buildings. So the future isn't one building or one technology, it's integrated, it's district level solutions that balance supply, demand, and the resilience. And with that, we'll shift to Jeff to walk us through details around district energy. Thank you.
Thanks, Gina. So just talking a little bit about district energy and what they are. So just to explain, essentially the 3 ingredients of a district energy system from a fundamental perspective is a source, so an energy center that could be multiple forms of energy generation, a distribution network, which is often piping underground, but could be in tunnels, and then the end user. So this is connected buildings. And these buildings could be a wide variety of types of buildings. It could be residential, commercial, healthcare, lab, data center, what have you. When it comes to why district energy, and Gina hinted on this already in regards to the opportunity to use a variety of energy sources, but really the first point is load diversity, the opportunity that the connected quantity of loads for all the buildings, technically that peak would never happen all at the same time for all buildings. And one of the goals is to have a diversified connection portfolio so that buildings that are peaking at different times, there's an opportunity to optimize the system selection and sizing so that there's a quantity of scale benefit to having a district system. another interesting benefit is future proofing. So by having centralized or fairly centralized systems, the opportunity to replace a system with something that is new or that is coming out that maybe even hasn't been invented yet, but we're seeing so much technological improvement in this sphere that adding that to a system that could then impact a large quantity of buildings at scale. There's a huge potential for that as long as those systems are set up appropriately to be able to handle some of those upcoming technologies. And we'll talk about that in a moment. Another opportunity is gathering energy from very much site-specific locations. We'll talk about this as well, but really, being able to harness energy from bodies of water or waste heat locations that are geographically, let's say, locked within a particular area, and then being able to share that out in a wider network. And then, of course, the opportunity to maximize buildings. So being able to connect to a district system can reduce the amount of space needed for mechanical systems within buildings. And as well, as Gina pointed out in our earlier moment, that the potential of freeing up rooftop space for other uses, tenant uses, etc. District energy systems have gone through a number of iterations over the years. Early systems were from the 1800s and primarily heat and steam driven. But then over time, opportunities and efficiencies have come forward. So, first generation, as I mentioned, heat and steam. Second generation, again, still high temperature, generally heating. And then once we move into the third generation, that's when heating and cooling and the discussion of even further reducing those heating temperatures became possible. Fourth generation is probably the most common in North America at this point, where you have heating and cooling, still relatively warm temperatures, but the opportunity to have so much more technology added as generation sources, energy storage, etc., to be able to support those systems. Most often, these are a 4-pipe system, and then there's a 5th generation system as well. When it comes to the 4th generation, as I mentioned, it's really a 4-pipe system that we commonly see. So this is heating supply and return and cooling supply and return. And oftentimes these are coming from a central energy station, and then they are delivering that energy to buildings. So, very much what you would think for in regards to like a water network or something like that, where, there would be metering for monitoring the energy use at each of the buildings. We call these energy transfer stations. For the 5th generation, this is really the most current iteration, if you will, of district energy. And really, it speaks to the opportunity of really lowering the temperature of the circulating loop to essentially an ambient temperature or slightly above ambient if necessary. And this could be a single pipe installation or a 2-pipe system, supply and return. But it really accommodates, by lowering that temperature of the loop system, the opportunity adding so much more opportunities for energy generation, waste energy capture, and reusing that energy so that it can support buildings. So that's the big opportunity with this newer system, and as well energy sharing. So what you could have is buildings that are high energy users that are actually, let's say, heating and cooling at the same time, or requiring cooling energy even in the winter. And so the opportunity to share energy that is not needed, rather than it being just lost to the atmosphere, to be recouped and shared within a network, is that same possibility. So things like data centers, labs, hospitals. So as I was mentioning, there's a lot of sources that can be considered for district systems, especially depending on the type of system that we're speaking about. So when it comes to dispatchable sources, so these are generally equipment-based sources. That's things like combined heat and power. That would be things like absorption chillers or heat pumps and chillers and basic equipment. But then we also look at other technologies and opportunities, and we look at things that have different timing considerations. So some things like geothermal have a very constant and steady potential for energy creation and generation. But then there's variable ones as well, like solar, where the sun is only up a certain amount of hours. So considering both of those things, as well as wastewater to heat energy, which is also a variable source. And then just within this graphic, we also identified the different temperature profiles that would exist within the different types of energy sources, as well as whether they're electrified or not. When it comes to the distribution system, again, fourth generation versus fifth generation, we're often seeing a comparison between 2-pipe and 4-pipe, especially when it comes to business cases for these systems. So just some benefits and limitations that we wanted to mention here. 2-pipe, like I mentioned before, high probability of increasing the amount of waste energy opportunities for use within the system because it's such a low temperature system. That can exist in the 4-pipe system as well. But generally speaking, in a 2-pipe system, because it's an ambient loop, that often means that it could be, high density polyethylene piping. It would be uninsulated. So there could be some savings, even just because it's 2-pipe versus 4, as well as less centralized equipment. But then, at the building level within a 2-pipe, you are looking at more equipment at the building level, such as a heat pump that would be able to elevate the temperatures to either a heating or cooling setting as required for the building. Whereas the 4-pipe, really it's improving the temperatures in a centralized location and then sharing that energy out. So it's a much easier impact to the buildings. So a new building can accept and anticipate certain temperatures within their distribution system. So that can make it a little bit easier from a planning and implementation perspective. When it comes to what the design of a district system looks like, there's a number of things to consider. So, as I mentioned before, really looking at the energy sources. So when we're looking at a grouping of buildings, whether they're existing or if it's a plot of land that is waiting for development, trying to look to see, okay, where are there opportunities on the site? Are there adjacencies of waste energy that could be harnessed to support energy and circulating that energy throughout a system? Similarly, grid connection. Well, there's a special slide specifically about it, but most of these technologies are electrified. And so looking at the opportunities of, okay, what can the grid handle? Is there energy storage that's necessary? And we'll speak a little bit more about electrification shortly. Then we go to distribution and control. So oftentimes, looking at the piping network, deciding what the right piping system is, and then looking at the control mechanism so that it can be highly efficient, as well as regulated or having certain amount of energy feedback and billing cycle information. And then resiliency and redundancy. So, oftentimes buildings, they want to have reliance on these district energy systems, and that's reasonable. Having backup systems in a centralized location really is a strong benefit because those backup systems can be sized and managed and maintained in a centralized location well beyond what could happen at the individual building level. And then at the same time, it's the piping system underground is a very resilient system to begin with. So we see the potential for redundancy within district systems really is a positive for these systems. We really find that when it comes to the design of these systems, they generally become quite customized. So not every district system is alike. There's nuances between each one of them. But there is possibility of interconnecting systems through time and evaluation. But generally speaking, there is custom engineering and it's not a one-size-fits-all scenario. And then when it comes to retrofitting and adding existing buildings to a network, you're really looking at compatibility of the building. So in a lot of cases, buildings, if they're operating at really high temperatures for heating specifically, there may be some adjustments that are needed to try and bring those temperatures down to be compatible with a system. Similarly, ideally the system in the building is already fairly centralized and even a hydraulic basis so that those systems could be tied into a network system. And we've done this in the past. When it comes to integration with the grid, there's a lot of constraints within our grid these days. Everything is trying to be electrically driven, and so it's causing shortages. When it comes to the systems that we're speaking about here, and really the leading solutions for generation, these are often very high performing systems. So high performance, which really can minimize the impact to the electrical grid as best as possible from an electrification perspective. Similarly, by having a district system, the opportunity to store energy or create energy in off-peak scenarios is very much a possibility, and then being able to share that benefit out. So, looking at energy storage, that can be a challenge from a space perspective within individual buildings, whereas when you're looking at it from a network, the possibility of having that energy shared and stored is much greater. And then, of course, there's just general benefits in regards to trying to manage electrical generation and connection. So even many of the larger district systems are looking at multiple connections to different switchgear or substations within the electrical network, so that there's even resiliency from that perspective, that if some of the network goes down, you still have a backup feed. Again, looking at some of the sources. So the steps that we typically take, looking for a carbon-free source to begin with. So this could be geothermal, solar, waste energy, like I mentioned, from external sites or even from the ground. Then we look at load profiling, and there's a lot of different techniques for this in regards to trying to understand the connected building potential and what those loads could look like. And trying to understand, okay, what could the diversified load be for a particular system and grouping of buildings, because there really is that opportunity to have a diversified connection. You look at modularity, and so similar to what Gina was speaking about earlier on, and even looking at the financial challenges with implementing systems like this, it is possible to grow these systems over time and phase them into implementation. There's a variety of strategies with considering even a nodal style district system, which is essentially smaller energy systems serving groupings of buildings, and then starting to connect those nodes together. And so that can accommodate growing these systems over time, where your capital is only being spent in chunks that are more incremental versus all at once on day one. Peak management really is speaking to diversification, but also the possibility of having energy storage. And then when it comes to the optimization, again, this is really speaking to, okay, are there strategic buildings that need to be connected? This could be either new concept buildings or existing buildings, as well as, are there those energy sources that are key sources that we want to have available to this network? So some of the opportunities of today, because the next section is going to talk a little bit about technologies, but also some of the case studies that we have. But the opportunities that we see for today, there really is a strong sustainability opportunity for district energy. Decarbonization of a large grouping of buildings at once is a really significant way of making an impact. So that's a huge driver of the opportunity. That's for today and for in the future as technology improves. But you look at smarter operations, having renewable sources and waste sources as part of these systems, it really starts to make a compelling argument. Technologies that we're seeing as well. So directional drilling is starting to reduce the amount of impact of having these systems in place. So, when you're looking at new installation and there's a lot of disruption within existing, campuses or cities, and if that can be reduced through directional drilling versus, trench excavation, there's a lot of benefit. And then, of course, some advent. A lot of the earlier district systems were steel piping, and that is still used significantly throughout North America and Europe right now. But high-density polyethylene piping is also something that is very much mainstream, and another opportunity for piping where, pipe can have small radiuses within the system, and it can reduce the quantity of fittings that is required. So just looking a little bit at technology and some of the case studies that we've had the privilege of working on. I'm sure you've heard of geothermal or geoexchange. Just want to talk on this a bit because it is a bit of a hot topic. Basically there's two opportunities when it comes, it's either closed loop or open loop. What we typically find from a closed loop perspective is this could form in a more horizontal heat exchanger arrangement. So, the network is more horizontal and shallow, if you will, and then vertical, which is, again, what it means. Vertical is more long and deep boreholes that form a field. And these fields can look like a lot of different things. There are opportunities of having fields below buildings, built within the foundations of buildings, on angles around buildings. So lots of creative ways of doing systems like that. And then, of course, there's the deep earth geothermal or aquifer geothermal, which are more open loop systems. Deep earth geothermal is definitely something that's possible, but it's a little bit less common. The open loop aquifer is really becoming a much more mainstream, and it definitely has a strong business case potential just because the amount of boring and drilling that's required is significantly less. Another technology that really is moving forward quickly within North America specifically, but also into Europe, is wastewater to energy transfer. And so really this is recovering waste energy, which is a constant temperature from the wastewater stream. So that could be connection to a sanitary system that is either pressurized or gravity fed. It could work with either or, and then usually involves some pumps and a holding tank and some filtration. And a heat exchanger, of course, and then from that harnessing energy. And again, that can work in summer, that can work in wintertime. There's many case studies already in use within Canada and the US, where then that energy is shared out to buildings. And then within the buildings or even within an energy center, those temperatures are elevated with a heat pump to then serve those buildings with the temperatures that are needed. Some of the interesting projects that we're working on right now that are very similar to what we're speaking about today. So in Ann Arbor, Michigan, we're working on a district energy community scale system. This is 3 different systems that we've been evaluating and really looking at the potential of connecting those to existing buildings. One of those systems is the downtown. The other ones are more in the rural areas of the city. But looking at geoexchange as well as the wastewater to energy transfer as some of our generating sources. And then, through this is the picture that we're showing here is energy modeling and essentially an energy map of the energy needed for building use within the entire city. And it's an interactive map as well, using a GIS platform that we created. And then, through this, a lot of community engagement discussion. There was review and consideration in regards to environmental and social justice, just in regards to, how can clean energy provided to the community. We're also doing a really interesting project in Berlin, New Hampshire. This is a new system as well. It is harnessing waste energy from a biomass electrical generation plant. And that waste energy is going to form a new district system, primarily used as a snowmelt system. So it's reducing the amount of salt that will be used within the city. It'll be reducing the amount of snow clearing that's required because it is a more mountain community. But it also has the potential of being used as a district system for buildings. Oftentimes within these district systems, and especially on university campuses, they come together with a microgrid. And so the potential of having electrical generation and electrical storage that's tied to these systems is becoming quite common. Combined heat and power, where electricity is generated and then waste heat is captured, is very common in district systems and is considered a very reliable source for electricity creation and then thermal energy as well. So this is just an example of a large cogen system that was installed, including battery storage, black start capability in regards to a campus. Another interesting project, so this is an inner city, but it's essentially green/brownfield development, 300 acres development, again, cold climate. And in this case here, we're looking at a clean energy strategy for the this large development, and really looking at a variety of sources. And in this case here, one thing that became very apparent is the large trunk sewer main that was running along the side of the property that could be used for wastewater to energy transfer. That connection point we predict would provide about 35% of the energy that's needed for the community. And this is a fairly large community, with the remaining coming from geoexchange. And then for this site in particular, we're adding in solar and a microgrid design with battery storage. So it can be fully independent if necessary. Another interesting project, this is one that is nearly complete. Substantial completion is actually this month. But in the city of Ottawa, which is in Canada, this was a large district energy modernization. It was 5 legacy district systems that connected over 80 buildings. A lot of these are the Canadian government's federal buildings, so they own and operate a lot of these buildings. And really, there was an evaluation of a variety of different technologies supporting this system. Stantec was involved in a lot of those different stages, as well as preparation of the buildings for connection, because one of the primary goals was interconnection of these systems, but also reduction of the temperatures, especially the heating temperatures, so reducing it to a low temperature system, and then improving the cooling temperature performance for the buildings. So a lot of work was put into updating the buildings so that they could receive this new temperatures from the system, as well as, like I was saying, the interconnection between the systems. And then the last project that I wanted to profile was Sinoc, which is in Vancouver, BC. This is a new system presently under construction. It is serving over 6,000 residential units planned for this development, and it is harnessing energy primarily from the wastewater system. It's a force main within the system, but it's elevating the temperatures with heat pumps and then serving those buildings throughout this area. So, it's a large development, and it really it shows the impact of the potential of using waste energy as a source for these energy systems.
Thank you, Tina and Jeff. We'll spend the remainder of our time together answering questions from the Q&A. If you have questions, please feel free to continue to add them to the Q&A section of this meeting. See some of the questions we have. First question I see here, what are the advantages of integrating district energy systems into retrofit projects compared to upgrading buildings individually?
Yeah, I think I'll take that one. So, sorry, could you just repeat that one again? I'm not seeing the question in my chat here.
Oh, sorry. What are the advantages of integrating district energy systems into retrofit projects compared to upgrading buildings individually?
Yeah, I mean, both have their challenges for sure when it comes to retrofits. As I was saying, I think the opportunity of retrofit from a district perspective is that you really could harness waste energy from a particular location. So, when you think of an individual building, it's in its location, right? It is locked within its area. And so whether or not it can receive waste energy can be very limited. So tying to and creation of a district network that could harness waste energy is really one opportunity. And then, as I was saying as well, the amount of investment in at least generating equipment would be reduced if you get to a scale that would allow for diversification of those loads. So there is a cost to creating the distribution lines to connect these buildings up. But generally speaking, at a certain scale, it becomes, the business case does prove itself that it works. And then I think the last thing I'd say is that when it comes to technology, having the ability to integrate new technologies into those systems in the future, 10 years down the road, the possibility of adding something that could impact all buildings in a flexible way is quite possible within a district system. Within buildings, you may not have that opportunity, or you may be very limited by the systems that are capable just because of the size of the building and the limitations of the building and the land that the building is on.
Thank you. Another question that came up are, what kind of tools are being used for model urban scale modeling, urban opt?
So we're using a number of tools from a modeling perspective. I'm not familiar with urban opt, so maybe if you can ask that question again or type in a little bit more on that. But yeah, we've been using a few different things in regards to, let's say, energy modeling. We use IES quite a bit, but then we've been using some of the Comstock and ResStock tools that are publicly available within the United States. That's what helped us for the Ann Arbor project. And then what we did is we tied it to a GIS model. So all the data was pulled into GIS to create those maps. So it's an interactive map of data and information. And then we're actually pulling that kind of a model into some of our other softwares that are more district energy focused in regards to defining and designing a utility network.
Awesome, thank you. Do you have project-specific info on business case, payback periods, value add to the building's value, etc., that you could share?
Yeah, I mean, it really depends, which is not a great answer. But and Gina, feel free to jump in here too. It doesn't. So far, I've been taking most of these. But
no, please go ahead. Yeah, thank you.
Yeah, I mean, we look at business cases many times in the different projects that we're working on. In some cases, we find that the cost to implement a district system versus building retrofits are nearly the same, one way or the other. But the future potential of a district system outweighs the potential of the buildings on their own. So that sometimes can move things forward. Of course, there's grants as well that would support implementation of these systems that are more on the commercial scale and trying to push those systems forward. But I think, the biggest opportunity we find is on the waste energy side and really harnessing waste energy where possible. It really does become cost effective in many of those cases if the opportunity presents itself. But it's not a simple payback discussion, right? You have to look at it a little bit bigger picture, where generally speaking, most of our evaluations are looking at it from a 50-year perspective, just because a lot of these systems, when you think of geothermal, they have easily a 50-year lifespan for the majority of the materials that are in place.
Thank you. All right, in the two-pipe system, fifth generation district energy system, what kind of strategies, tertiary systems at the building level are used to bring the building up to temperature set points? And if the loop is changing from heating to cooling?
Yeah. So, I mean, generally speaking, it's a heat pump at the buildings. If it's a switchover system, that gets a bit complicated. Generally speaking, those fifth gen systems are an ambient loop, so slightly elevated above the ground temperature or near the ground temperature, and so then the heat pump could within those systems either create heating or cooling or both. depending on what the needs are for the building. So that's typically what we see. And that could look like a centralized heat pump. It also could look like distributed heat pumps. So for instance, in residential, that could be distributed heat pumps for each of the different units.
Yeah. Sort of a statement and question. The biggest challenge I faced operating district cooling plants in the Middle East is demand charges and penalty for not being able to maintain delta T due to variable load in buildings and not installing PICV for AHU and MAU. How do you suggest mitigating that, controlling the flow of the water, and on the tertiary side of the system, i.e. secondary side of the heat exchanger building side, are controlling flow based on the input side, then it leads to temperature issues as controls don't reach fast enough?
Yeah, so low delta T syndrome is a real thing. We had a lot of fun with that, especially for the Ottawa project. I've presented a few times on some of the strategies that we use to improve chilled water delta T for buildings. It does align with everything that you're talking about. So installing pressure independent control valves is, has been very helpful. There's a variety of options out there, but that has been very helpful. But we even looked at and variable flow, of course. So having VFDs on the pumps and having those pumps actually capable of dropping to the lowest flow possible in scenarios that call for it. Oftentimes we find that pumps can be oversized. So those are all tertiary considerations, and that can be complex when it comes to the buildings, because the buildings may not understand why they would need to do this or have these systems installed. And then we also did look at reset schedules, and that seemed to have a pretty big impact to how the buildings performed. But we were able to get significant performance improvements with installation of pressure independent control valves, with having those reset schedules, VFDs on the pumps, and essentially retro commissioning of those systems so that they were functioning correctly. I can't stress that enough. Unfortunately, systems, once they get designed or even after they're implemented, they don't often run the way that they should. And so having them commissioned and looked at over time, because our operators, they're trying to do what they can. They're trying to navigate the different complaints that come from building users, but sometimes those systems can move out of what their original intent was. And so recommissioning would really be a benefit, and we found that quite valuable.
A few other questions. Do you have any brownfield case studies that successfully implement a microgrid strategy?
So I'm more of the thermal guy and not the microgrid guy, but I'll do my best. Yeah, so we've implemented and we are evaluating microgrids in a number of places. Generally, these are campuses with single ownership of buildings. So, not necessarily like from a city perspective, but, like I said, a campus perspective. But yeah, they have been implemented in existing sites for sure. And oftentimes what we find is that initially they may not be prepared for like a complete black start. So basically, like if there's a full power outage, that they can start up on their own. And then sometimes we're coming back and retrofitting those sites so that they can be black start capable, and then operating in a way that would really provide a full backup power and an islanding of the electrical grid for those connected buildings.
Thank you. We have one more follow-up to the question regarding project-specific info on the business case and payback periods. The follow-up is regarding the value added. Do you consider the impact of retrofit or district energy systems on total appraisal value in future years when considering the 50-year time frame? Or the clients do not necessarily take those into account and rather look forward to maximizing the grants and reducing costs.
Seems like there was a few things in there. I don't know if we really consider like from an appraisal perspective. I've not seen that included in any of the analysis that I've seen or been a part of. It's a good idea. I think generally speaking, and Gina kind of spoke to this too, like the building improvements and having these buildings not being something that's left behind, but is modernized to be able to support these new technologies will add asset value. And so that is, you know, a consideration. Gina, sorry, I know you were going to try and say something there.
Oh, no, that's exactly it. I would just add mostly the focus is on securing grants and incentives if those are available, operational cost reductions. They think of lowering the energy bills and maintenance costs, and then meeting their carbon targets. We know that a lot of portfolio organizations, they do have specific carbon reduction targets or regulatory requirements. So this is where we think of district energy systems or system that would really help them get there quickly and cost effectively.
Thank you both. All right. I think that's it for questions. Thank you for joining us for today's session and for participating in our 3-part webinar series, The Transformative Potential of Sustainable Building Retrofits. By scanning the QR code, you'll gain access to the recordings from the series. We hope you found the content valuable, and we look forward to connecting again soon. Thanks, everyone.